I have a feeling this is going to be a couple of videos, or I could just make one giant one as a test of endurance, but let's not. In the last section, we looked at partial derivatives. Partial derivatives went only in the direction of x or y. We didn't consider partial derivatives in directions other than in the x direction or the y direction. But suppose we were standing on top of that mountain like I had in that picture, or down the valley like I had in that previous picture, and I wanted to figure out what was the slope going in a certain direction. For this, I need what we call the directional derivative, and the gradient is part of it. So in the PowerPoint slides, I laid out the whole process about starting with a point and a unit vector and working your way through until you come up with the directional derivative. So this thing here is the directional derivative in the direction of u, where u is some unit vector, and the fact that it's a unit vector is important. You end up with a couple of things. The AB is a point. That u is the direction vector. So you want the derivative in a certain direction. That vector u1, u2 will give you the direction. And then what you end up with is the partial derivative of x, the partial derivative of y, and a dot product. Not just a multiplication, a dot product between the directional derivatives and the direction vectors. So let's try a couple of these. Like I said, the PowerPoint has all the information as to how I came up with this. I did not just invent this. But let's work through a couple of problems that deal with that. So we know that we're going to have to come up first with a vector that represents the partial derivative of x and partial with respect to y. So if I take the derivative of xy with respect to x, I just get y. If I take the partial derivative of xy with respect to y, I just get x. Okay. I'm going to take the dot product of that and the direction vector, which is 1 over root 2, 1 over root 2. Now, it happens that I know that this is something that's of magnitude 1, right? Take a squared plus b squared. I'll get a half plus a half, which is 1. Square root of 1 is still 1. But you should always check your direction vector to make sure that it actually is a unit vector. Now, in this case, we can substitute pretty quickly. If we're talking about the ordered pair 2, 1, then y is equal to 1, x is equal to 2. Take the dot product of that with 1 over root 2, 1 over root 2, and I get 1 times 1 over root 2 plus 2 times 1 over root 2, and that gives me 3 over the square root of 2. So 3 over the square root of 2 is the rate of change, or the slope, in that direction. What is that direction? Well, it's a 45-degree angle, right? 1 over root 2 this way, 1 over root 2 that way. That's my direction vector, okay? Directional derivatives. Let's take a look with something that has some trig in it. I want to find the rate of change of f of xy equals 2 times the sine of x minus y at the point 0.33 in the direction of theta equals pi over 6. So the first thing is, I need to start by finding a direction vector. How do I find a direction vector? Well, the direction vector on the xy plane goes cosine sine. Cosine is the x-coordinate, sine is the y-coordinate. In terms of pi over 6, the cosine of pi over 6, go back to unit circles trig. Square root of 3 over 2. The sine is equal to 1/2. Is that a unit vector? Sure. 3/4 plus 1/4 is 4/4, which is 1. It would make sense since these things are part of the unit circle. Unit circle has a radius of 1, so there we go. So the next step then is to find partial derivatives. So the partial derivative of f with respect to x is going to be what? It's going to be 2 times the cosine of x minus y times the derivative of the inside with respect to x. Well, when I derive the inside with respect to x, I get a 1 there and a 0 there. So it's just that times 1. The partial with respect to y is, again, 2 cosine of x minus y, but this time times the derivative of the inside with respect to y, which is negative 1. All right. It might help us to do some evaluating here rather than do the dot product. So if I do some evaluating here, the partial derivative with respect to x at the ordered pair 3, 3, right? That's my A and my B, is going to be 2 cosine of 3 minus 3, which is 0. Cosine of 0 is 1. So that gives me 2. Partial with respect to y at 3, 3 is going to give me 2 times the cosine of 0 times negative 1. So negative 2 times 1 is negative 2. Okay, what I'm left with at this point is just that dot product. So I can take the dot product of 2, negative 2 dot the direction vector, root 3 over 2, 1/2. Okay, so 2 times square root of 3 over 2 minus 2 times 1/2 gives me square root of 3 minus 1. Done. That's my slope. All right, so that's the rate of change of that function defined in terms of x and y at the ordered pair 3, 3 in the direction of theta equals pi over 6. And the first thing I did to achieve that was I turned it into a unit vector. All right, at this point, it's time to introduce something we call the gradient, which we've already been using without calling it the gradient. The gradient is just a vector of partial derivatives. So the partial with respect to x, partial with respect to y. If you're in R3, you can have a partial with respect to z. The funky notation is an upside-down triangle. Upside-down triangle is the gradient, partial x, partial y, which means that we can rewrite the directional derivative formula as the gradient of f dot u, right? Still a dot product, but now we can call it the gradient. So the gradient of the function dot the unit vector that tells me in which direction things are going. All right, so let's try a couple of these. The first one up here says find the gradient for f of xy equals 4x squared minus 2xy plus y squared at the point negative 1, negative 5. This just means we want the partials. Right? We're not finding directional derivatives here. We're just being asked to find the gradient. So the gradient for f evaluated at xy equals the partial of f with respect to x. So here I'll end up with an 8x. If I take the partial here with respect to x, I get a minus 2y. And then the derivative of y squared with respect to x is just 0. All right, partial with respect to y. The first term is 0. The next term will give me a negative 2x. And the third one will give me a plus 2y. And now all I have to do is put in the values that I was given. So 8 times negative 1 is negative 8. Negative 2 times negative 5 is positive 10. And then over here, negative 2 times negative 1 is positive 2. 2 times negative 5 is negative 10. So the gradient is a vector. And if I put in values for x and y, it's just a vector of constants. 10 minus 8 is 2. 2 minus 10, negative 8. That's the gradient. Now the next question kicks it up a little bit. It says find the gradient and the directional derivative for f of xy at a given point in this direction. First of all, is this a unit vector? I think it is. It makes a 5, 12, 13 triangle if I'm looking at it right. 5 squared is 25. 12 squared is 144. 13 squared is 169. Sure enough, that's 1. All right, so that vector here is already a unit vector. We're in good shape. Let's come over on the side here, and I'll rewrite the function. The function I was given was f of xy equals 3x squared plus y to the third. So the gradient of f is going to be what? It's going to be the partial with respect to x. So 6x, there's no y term in there. And then the partial with respect to y, the first one drops out, and we get 3y squared. So now if we want the gradient evaluated at 3, 2, which is the point that I was given, the gradient evaluated at 3, 2, 6 times 3 is 18. 2 squared is 4 times 3 is 12. So there's my gradient evaluated at 3, 2. Now if I want the directional derivative in the direction of u should be the dot product between 1812 and the directional vector that I was given, which was 5 over 13, 12 over 13. All right, so I end up with 18 times 5 over 13 plus 12 times 12, which is 144 over 13. 18 times 5 is 90. 90 plus 144 is 234. Grab a calculator. If I take 234 and divide it by 13, you know that comes out to be a whole number. It comes out to be exactly 18. So 18 is the rate of change in the direction of u. So that's the rate of change in the direction of that particular vector. That vector that goes 5 over and 12 up. As you read through the notes, you'll notice that there's a second formula that I came up with for the directional derivative. And that is, I went through a process of using the dot product formula involves cosine, right? If you were finding the angle between two vectors, you could use a dot product or you could use the cosine formula. Well, using that cosine formula leads us to a slightly different definition of the directional derivative, and that is we can take the magnitude of the gradient and multiply it by the cosine of the angle between the two vectors, assuming that we know what the angle between the two vectors is. Now, why is that helpful? Well, I've listed out a couple of things there. If the angle is 0, cosine is 1, that's when the directional derivative has its highest value. In other words, the greatest rate of increase happens when the direction vector and the gradient point in the same direction. The opposite is what happens if the cosine is -1, the angle is pi, and that's the greatest rate of decrease. So you've got to get three things out of this little slide here. One of them is, how do you find the greatest rate of increase? Same direction as the gradient. Greatest rate of decrease? Opposite direction. How about the place where the rate of change is 0? That happens when the gradient and the unit vector are perpendicular to each other. So you may get vectors, and then you have to point them in the right direction to find the place where the rate of change is 0 and where the greatest increase is. All right, let's take a look at an example. This one I got a lot of questions for. I want to find a gradient. I want to find a gradient at a point. I want to find the vector describing the steepest ascent, the steepest descent, and the vector that shows no change at a point. It's actually not a terrible problem. If I want to find the gradient, then I need to find the partial derivatives. So here, let's put the gradient in terms of variables up here. All right, take the partial with respect to x. I'll get 2x. Take the derivative of the second term with respect to x. I get 4y, and the third piece just drops out. Now, take the partial with respect to y. First term drops out. Second one gives me a 4x. Third one gives me a minus 2y. Okay, so that's my gradient. Find the gradient at 2, 1. Well, now put some numbers in. The gradient of f at 2, 1 is going to be 2 times 2, which is 4. 4 times 1 is also 4. Over here, 4 times 2 is 8. 2 times 1 is 2. So I come up with the vector 8, 6. That's the gradient evaluated at 2, 1. The third question says find the vector that describes the direction of the steepest ascent. Well, the steepest ascent has to go in the same direction as the gradient. So if the gradient is 8, 6, can I create a unit vector in the same direction as 8, 6? So if I want ascent, I want same direction as 8, 6. Well, 64 plus 36 is 100. Square root of 100 is 10. So take 8 divided by 10, 6 divided by 10, and simplify that. So I come up with the vector 4 over 5, 3 over 5. All right, so find the magnitude of that vector. So find the magnitude of 8, 6, and then divide it by its own magnitude, and you'll have something that goes in the same direction. Hey, how about the steepest descent? Steepest descent goes in the opposite direction. So if I know that this is the unit vector that gives me the steepest ascent, then the unit vector that gives me the steepest descent is the opposite of each one. And then what's the vector that gives me no change? Well, it's got to be perpendicular. How do I figure out a perpendicular vector? So if I've got 4 over 5 and 3 over 5, you realize that two slopes are perpendicular if they're opposite reciprocals of each other. Opposite reciprocals means flip them around, change the sign. So if I flip them around, make it 3/5 in the first coordinate, 4/5 in the second coordinate, and change the sign, I'll end up with something that's perpendicular. Is that the only possible answer? No. I could have made the 4/5 negative also, okay, and that would have achieved the same goal. How can I check my answer to see if I'm right? Take the first vector up here, and this vector down here, take the dot product. 4/5 times negative 3/5 is negative 12/5. The other two coordinates multiply to be positive 12/5. Add them together and you get 0. Therefore, you've come up with something that's perpendicular. Dot product equals 0 is always a quick way to check. All right, let's try another example. Here's another question. Here's a point. Find the steepest ascent, steepest descent, and no change. So again, we'll start with a gradient. The gradient of f is going to be derived with respect to x. I get 8x. Derived with respect to y, and I get 6y. All right, this is starting to look similar. Evaluate it now at 1, negative 1, and I get 8, negative 6. So the steepest ascent is simply going to be in the same direction. So 8 over 10 is 3/5. Nope, 8 over 10 is 4/5. Negative 6 over 10 is negative 3/5. So that's the direction of steepest ascent. Then if you want steepest descent, take the opposite. So I'll get negative 4/5, positive 3/5, and then no change would just be the perpendicular. So switch and change the signs. So maybe make it positive 3/5, positive 4/5. Sometimes you could put a plus minus in the front here. That plus minus just indicating that it could actually go in either direction and you would still be okay. All right, let's take a look at this one, and then I think we'll split this second part into another video because this is starting to get long already. If we want to talk about the angle measure from the positive x-axis, I've got a function, I've got a point, and I want to find the angle measure that produces maximum increase, maximum decrease, and no change. In order to do that, you're going to have to eventually write that directional derivative in terms of theta, and then find the angle of theta that maximizes the function that you came up with. So, first step is, let's find the gradient. Leave that up there in the corner. The gradient of f is going to be the derivative with respect to x. So 2x. Oh, and the derivative with respect to y is just from that middle term, 6y. So that must mean that the gradient of f evaluated at the point I was given, which was negative 3, negative 1. 2 times negative 3 is negative 6. 6 times negative 1 is also negative 6. Okay. There's my gradient. This is good. How is this helpful? Well, where is negative 6, negative 6 from the origin? It goes 6 to the left and 6 down. So it's down here in the third quadrant. And you notice is one of those that splits the quadrant exactly, which must mean it's easy to find the angle measure. What's the angle measure for that? Well, it goes from here all the way down there. that theta value must be 5 pi over 4. Right? 4 pi over 4 would be the axis, so add another pi over 4, and I'm at 5 pi over 4. So the maximum increase must happen at theta equals 5 pi over 4, in the same direction as the gradient. Maximum decrease is the opposite of it. So 5 pi over 4 goes down to the left. Which is the one that goes up to the right? Well, that's pi over 4. So maximum decrease will be pi over 4. If you want zero change is perpendicular to both of them. So perpendicular to both of them would be coming out this way or down that way. So this guy up here is 3 pi over 4. This guy down there is 7 pi over 4. So no change would be theta equals 3 pi over 4, 7 pi over 4. All right, and then I had an alternate way to do this. Suppose instead of just looking through my coordinate axes, I wanted to write the directional derivative in terms of theta. So I'm going to start with my unit vector. My unit vector as cosine of theta, sine theta. And we knew that the gradient, it's a terrible gradient. There we go. The gradient is -6, -6. So now take the dot product. Take the dot product of the gradient and that unit vector. And I end up with -6 cosine of theta minus 6 sine theta. Let's call that g of theta. And let's take the derivative of g of theta. So g prime of theta is going to be, well, the derivative of cosine is negative sine. Negative times a negative is a positive, so I get 6 sine theta. The derivative of sine is cosine, so minus 6 cosine theta. You know that you hit a max, or you may hit a max, when g prime is equal to 0. So when does this thing equal 0? The only time that thing is going to equal 0 is when the sine of theta is equal to the cosine of theta. Where is the sine and the cosine the same? It happens twice. It happens once at pi over 4 in the first quadrant, and it happens again at 5 pi over 4. Your goal then is to figure out which one's the max and which one's the min, because one is the max and one is the min. So if you evaluate the original function at pi over 4, you'll end up with a -6 times root 2 over 2, and then another 6 root 2 over 2. That'll give you a -6 times the square root of 2. It would then make sense that if I put in a 5 pi over 4, I'm going to end up with the opposite, because I'll end up with a negative root 2 over 2 for both of those coordinates, so that'll give me a positive 6 square root of 2. So without drawing my picture, I could have figured out that this was the max or the steepest ascent, and this was the min or the steepest descent. And I think the only other question it asked for was the magnitude of the gradient. Well, the magnitude of the gradient is just the magnitude of that -6, 6 that we came up with. So the magnitude of the gradient which we can write as the magnitude of the gradient at -3, -1 is just going to be the square root of, right, here's our gradient, right there, -6 squared plus -6 squared. So the square root of 36 plus 36, square root of 72. Hey, we can simplify that as 6 square root of 2. Hey, I've seen that number before. Didn't I see that when I was working with my g of thetas? And sure enough, the magnitude of the gradient is going to be the same as what I got for that g of theta function evaluated at its direction of steepest descent. All right. We'll work further on gradients and directional derivatives in the next video.